What's really going on in a chemical reaction? Why are reactions like a trip to Las Vegas? And how do molecules know what reaction they're doing? And how could you make your bicycle explode? Keep watching to find out. Before we start, some terms and conditions. To keep things simple, I'm going to use the word molecule throughout this video, but the explanation works just as well for atoms and ions. I'm also going to say species in place of element or compound, and I'm only going to use the word concentration even for gases. Well, alright. I'll use the word pressure sometimes. And I'm not even mentioning activity or fugacity, so physical chemists and chemical engineers, don't worry. Now, the history of studying how reactions happen goes right back 150 years before chemists even agreed that molecules were possible. At the time, the idea that chemicals were made of tiny particles was widely dismissed as ridiculous, which with hindsight seems strange now because we can't really understand chemistry without an understanding of molecules. In fact, the easiest place to start when talking about how reactions happen is with the kinetic theory of gases. The word kinetic comes from the Greek word for movement, and with gases it's very simple. Molecules fly about and randomly knock into each other. The higher the pressure of the molecules, the more often they knock into each other. If the wrong molecules knock into each other, there's no reaction. If the right molecules knock into each other, but the wrong bits hit, there's no reaction. If the right molecules knock into each other and the right bits hit, but they don't collide with enough energy, there's no reaction. So we only get a reaction if the right molecules bump into each other with the right orientation and with enough energy. So with just that simple theory, we can understand several things about how gas phase reactions happen. Higher pressures mean faster reactions because there are more collisions in any moment. Usually, the rate of the reaction will be faster for simple molecules than for more complex molecules because it's easier for simple molecules to collide in the correct orientation. So that also means that some molecules fundamentally react faster than other molecules. And reactions go faster at higher temperatures because the molecules have more kinetic energy for flying about, rotating, and vibrating, so they'll hit each other harder. But how do molecules know if they've hit the right molecule with the right orientation and with enough energy? Well, they don't. So let's go a little deeper. Let's start with the energy part first. Remember that molecules aren't hard spheres, but fluffy clouds of electron density around a tiny nucleus. At long distances, the molecules actually have a slight attraction for each other, and that's because the valence electrons on the outside are not distributed evenly, and they create patches of electrical charge that attract oppositely charged patches on other molecules. Then, the nuclei of each particle see the electrons on the other particle too, and that also generates an attraction. But as they come closer together, the repulsion between the electron clouds and the nuclei for each other gets stronger. Now, if they come together with low energy, we can simply summarize all those complex interactions by saying they bounce off each other. And in fact, we can model the whole thing pretty well by just pretending they're rubber balls. But at high energies, things are very different. The molecules are rotating and vibrating vigorously, meaning that bonds are stretched and vulnerable to breaking. The molecules also have enough momentum that the nuclei get pushed together hard enough to merge their electron clouds and distort their molecular orbitals. If you don't know about molecular orbitals, why not check out my video on that topic? And on top of all of this, the electrons can get kicked into excited states, populating antibonding orbitals that destabilize the molecules. With the molecules pushed together, electrons in the two molecules can join new orbitals that are created by the proximity of the colliding atoms. Then, as the nuclei start to repel each other, the atoms will recoil apart. But now there's a possibility that one of the new molecular orbitals will have a lower energy than the original ones, with different arrangements of electrons around the atoms. But most collisions don't create new lower energy bonding orbitals. Even with the same molecules, if the wrong atoms collide, they only result in non-bonding or anti-bonding orbitals that allow the molecules to separate again, as they were before. So all these factors together explains why molecules need to have both a high kinetic energy and the correct orientation for reaction. But how do they know what reaction they're doing and what the products are supposed to be? Well, obviously they don't, because they're molecules and they're stupid. In reality, these molecules are also breaking up and forming many different kinds of weird arrangements that we call intermediates. But high-energy intermediates are unstable. These intermediates are carrying so much potential energy, it only takes a small knock from something else to make them break up. And often that high potential energy comes from some weird arrangement that leaves atoms exposed and vulnerable to another molecule coming in to steal it. So all of this weird stuff happens until the atoms find themselves in a particularly low energy arrangement, which is another way of calling it stable, and those are our final products. So we have to adjust the temperature of the reaction to make sure that we've got enough energy to break up and rearrange as many of our reactants as possible. But once the products have been formed and lost their energy, as few as possible are going to get enough energy to keep reacting. And chemists can spend a lot of their time getting that balance right. I once had a reaction that was supposed to be really simple, and no one could work out why it wouldn't work. A couple of years later, I found someone that had made it work beautifully just by turning the temperature down about 25 degrees. All this means that some reactions are performed at 1000 degrees centigrade, while others are performed at minus 78 degrees centigrade. But can the reactants accidentally make the wrong thing? Yes. Yes, they can. In school and undergraduate teaching labs, we only use reactions that are well understood and work nicely. But in research, getting the wrong thing happens most of the time. It's a constant headache, and maximizing the efficiency of getting the right products is a major part of chemistry research. Now, most chemical reactions don't happen in the gas phase, so what happens then? In the laboratory, and certainly in living things, we do most of our reactions in solution. Solutions are much easier to handle than gases, and they usually react faster and more reliably than solids. So in solutions, we have our solvent and we have our reactants as some sort of solute that's free to move around in the solvent. In this simple model, everything works more or less the same as for gas phase reactions. The reality, however, is that there's a lot more jiggling about as solvent molecules get in the way or bond to the reactants or react with the reactants or even make cages around the reactants. But most of the time, we only need to worry about that if we're making detailed measurements or getting into the details of a reaction mechanism. But our choice of solvent changes the solubility of our reactants, potentially limiting their concentration, and they especially limit the temperature range at which we can perform reactions. But on some occasions, the exact nature of the solvent can interfere with the details of the reaction mechanism itself. And since many chemists forget about that, it can lead to a lot of wasted time. But for this video, we're just going to pretend that solution phase reactions work the same way as gas phase reactions. In other words, our reactants are free to wander about independently of each other and independently of anything else. Alright, so let's zoom out from our individual molecules and take a look at the wider picture. But before I get onto that, if you could just click the like button, it'll help us make more videos. Thanks. Now let's start by taking a look at the simplest situation where a molecule reacts all by itself. That might sound strange, but it's actually very common. A molecule might decompose and break up, or it might simply rearrange into a different shape, which might not be what most people think of as a reaction, but changing the shape of a molecule changes its chemical properties. For this demonstration, we're going to look at a Diels-Alder adduct. Now, I was going to talk about a bent form and a straight form, but that's just going to cause all kinds of trouble, so we're just going to call them the endo and exo isomers. Now, the molecule can flip from this endo isomer into the exo isomer. If we make a graph of the concentration of the endo isomer against time, we get this kind of boring graph. But what's really important here is the shape of the curve. It shows the endo isomer is decreasing exponentially. In other words, as the concentration decreases, the rate of the reaction decreases too. And the more the reaction slows down, the less the concentration decreases, so the longer the reaction lasts. And according to the mathematics of this curve, the reaction will continue until infinity, which is a great example of why you shouldn't take mathematical models too far. A more quantitative way of putting this is that if we halve the concentration, we get half the rate of reaction. And if we quarter the concentration, we get a quarter of the rate of the reaction, and so on. This is, very simply, the behavior that we get if the molecules flip after a random amount of time. But why should it be random? If they're all the same molecule, why don't they all flip at the same time? It's because they actually need to get enough energy to perform that flipping action. A little bit like flipping a light switch. They get that energy from randomly bumping into solvent molecules, some of which will give them a hard kick and get them to flip. And it's the random nature of that bumping that results in the flipping of the endo isomers also being random. This bumping is an example of something called activation energy, and we'll go into more detail about that in another video. But for now, it means that chemical reactions always go faster at higher temperatures, which is sometimes a good thing and sometimes very bad, but we'll get onto that later. Now, to see why this leads to an exponential decrease in reaction rate, let's imagine a simple case of 100 molecules. Let's say that in any moment there's a 10% chance that a molecule will flip from endo to exo. So in the first moment, that'll be 10 molecules flipping. In the second moment, it'll only be 9. In the third moment, it'll only be 8, and so on. Mathematically, that gives us the exponential curve. But in reality, it'll have discrete steps because you can't have a fraction of a molecule. And that's why reactions are like a trip to Las Vegas. They're all about chance and probabilities. If you understand that, you'll understand a key point about chemical reactions and chemical kinetics. Now let's look at another common situation in chemistry, which is a bimolecular reaction. In other words, a reaction between two molecules crashing into each other. And let's go back to our nitrous and nitric oxide molecules we saw from our early demonstration. Now, if we have equal concentrations of these two molecules, because it is a bimolecular reaction, we will get the same shape of curve whether we plot the concentration of nitrous oxide or nitric oxide, because every time we lose a mole of one, we also lose a mole of the other. Now, our curve looks similar to the case for the unimolecular Diels-Alder adduct, but with a slightly different shape. But now, if we halve either the concentration of the nitrous or the nitric oxide, we get half the rate of reaction. But why should that be? The total concentration of the reactants is 3/4 of what it was, so why isn't the rate of the reaction 3/4 too? Very simply, if we have half of the nitrous oxide, in any moment there are now half the chances for a collision with nitric oxide. But what happens if we now go the other way with the nitric oxide and double its concentration? Well, now, even though there are half the nitrous molecules, there are double the nitric molecules, and our probabilities of reactive collisions is the same as when we had equal concentrations. As I said, it's all about probabilities. Now, I'd always assumed that this relationship was one of the key bits of evidence for proving the existence of atoms and molecules back in the 19th century, but it wasn't. In fact, it turns out that Wilhelm Ostwald, one of the most prominent opponents of atomic theory, yeah, that one from my Avogadro video, was also one of the great pioneers of chemical kinetics, even though he didn't believe in molecules. Now, this ability to get the same rate of reaction by raising the concentration of one species while reducing the other is really important, because often one of our reactants is very expensive or rare. So if the other reactant is cheap, we can use lots of the cheap one and only a little of the expensive one and still get a useful rate of reaction. In fact, if we're lucky, we can even use the cheap reactant as the solvent, for example with water or acetic anhydride. And a useful rate of reaction is important. Sometimes because time is money, whether that is researcher time or energy for keeping the reaction hot and so on. And sometimes it's because we have to complete a reaction within a certain time for it to be effective. For example, with the catalytic converters in cars that reduce car pollution. So now we've looked at the basics of gas and solution phase reactions. Let's take a quick look at the mysterious world of solid reactions. Now, the mechanisms of solid reactions are very complex, usually involving decomposition of solid materials into mixtures of gases and liquids, or partial melting. So we're going to keep this really simple. With solids, the crucial factor determining reaction rate is not concentration, but surface to volume ratio. That's because the reaction can only happen where the reactants meet. This is one important reason that people usually grind powders as finely as possible before using them in chemical reactions. For instance, iron reacts with oxygen quite easily, but we aren't worried about our bicycles catching fire, are we? But when we grind that iron into a powder, things are very different. This is a hand warmer. It's a porous bag of iron powder, salt, and vermiculite. It comes in an airtight packet, and when you open the packet and expose the bag to the air, it gets quite warm for a few hours. So what's going on? Well, you probably know that oxygen and water make iron rust, and salt makes it rust even faster. For a car or a bicycle, that'll mean that you have to be careful near the sea, or it will suffer serious rust in just a few years. But this bag contains powdered iron, and powdered iron with salt, water, and oxygen will rust away completely in just a few hours and release a lot of heat as it does so. The vermiculite has two jobs. It's a mineral and it provides water that's trapped in layers between its crystals, but it also absorbs the heat from the iron. Absorbing the heat this way keeps the temperature down, which slows the reaction and keeps the hand warmer at a nice temperature for longer. But the dependence of reaction rate on surface area can have deadly consequences if we ignore it. For example, starch, which is the main component of flour, is flammable. But when you're at home baking bread, you don't need a fire extinguisher ready in case it suddenly explodes. And that's for the same reason that if I try and set fire to this iron powder, nothing happens. And that's because the surface area to volume ratio is so small, the reaction is very slow because the oxygen in the air can only get to the outside surface. On top of that, even though the outside surface is hot enough to react, that heat passes so slowly to the inside that the rate of heat getting to the center is slower than the rate of heat being lost to the surroundings. But if we separate the individual particles, things are very different. Now the particles have a much higher surface area to volume ratio. Firstly, that means that in any one moment, more oxygen can react with iron, but crucially now, the heat can pass right to the center of every particle much faster to create superheated gases that set the other particles on fire. Now the rate of heat being generated by the reaction is higher than the rate of heat being lost to the surroundings. That means the temperature keeps increasing, and that means the reaction rate keeps increasing, and that is what makes an explosion. This little demonstration doesn't look too bad, but imagine what it means for a large flour mill, where they're dealing with tons of flour flowing between silos and trucks for transport. These factories have to treat flour as a highly flammable substance that can cause explosions in the same way as flammable liquids. And it isn't just normally flammable materials like starch and wood dust that behave this way. Fine metal powders being used for making metal alloys can spontaneously catch fire. That's because most metals will react with oxygen, and when the particles are really small, just friction is enough to start a fire. You then get air currents suspending the powder particles in the air, and the whole thing goes up whoosh. These fires can be a major hazard for engineering laboratories. So that means that if you ground your bicycle down to a fine powder and set fire to it, it could explode. In fact, that's pretty much how fireworks get their sparkle. So there you go. That's the basics of what goes on inside chemical reactions. But there's lots more to it than that. In fact, I was planning to put it all into one video, but it turns out that rate equations, activation energy, transition states and intermediates all need videos of their own, so to be sure to subscribe if you want to catch them. And how about you? Have you ever exploded a bicycle? Let us know in the comments. And finally, this video was produced at Kyushu University in Japan. We have science and engineering courses in English, so check the description for a link, and I'll see you next time.